Okay, so assignment 3, question number 10. This is going to involve a number of consecutive calculations that we're going to need to put together our heat stress index. So it's easy to make a math mistake, a mathematical mistake as we go through this. So we're going to have to do this a little bit carefully. So first, let's read the problem. Using metabolic rate 800 BTUs per hour and the following data, calculate the heat stress index. And for our heat stress index, how are we going to calculate that? Well, heat stress index basically is the ratio of the maximum amount of cooling that you can get from evaporation in a certain work situation, divided into, or the ratio with the what you need to reject from the worker's body, and as a result of the amount of work that he's doing and radiation, convection, and so on. So this is the amount required, it's the amount of energy that the worker has to reject, and E max is the maximum amount of energy removal that you can get from evaporative capacity. So we're going to have to calculate this. The bottom of this is going to be pretty straightforward. We just really kind of did it before. E max equals 2.4 times to the 0.6 power times velocity of the air to the 0.6 power. That's in feet per minute. Metabolic rate is in BTUs times the vapor pressure of the water in millimeters of mercury. That's 42 minus whatever the ambient happens to be. And then we're going to combine, that's going to be the bottom of our equation. And the top of our equation is going to be a combination of metabolic rate, as BTUs, the amount of radiant heat that we're generating, and the amount of conductive heat that is going to be involved in the work that the worker is doing. Okay, so let's give this a try. It's going to be a little bit arduous, but if we go through it carefully, step by step, we have a pretty good shot of getting it to work for us. Okay, so I'm going to pick up my page and let's see. Okay, let's get started here. So I'm going to try and summarize this a bit so we don't run out of space here. The heat stress index is going to be equal to the E required over the E max times 100. I'm leaving the 100 out of this for the moment. Okay, so that's going to be equal to, and if we go remember what that was equal to, it was equal to the metabolic rate plus R plus C over, and let's calculate this right now. Let's calculate the maximum amount of cooling that we can get from evaporation. And that is going to be equal to, okay, Emax is going to be equal to 2.4 times the velocity, which is 130 to the 0.6 power, times 42 millimeters minus the ambient vapor pressure for water, which is 20. So that's going to be 22 millimeters. Okay, so that's going to be equal to, let's pull our calculator out. That's going to be equal to 130. Going to enter 130, go over to my x to the y, click, enter my exponent, 0.6, and it gives me my value, 0.6, and it gives me my value of 18.55 times 22 times 2.4. So my Emax is 979.5. Let's write that down. 979.5. 979.5. 979.5. Great. Okay, so my metabolic rate we already have that at 800. So I can really start to fill this in. So this is equal to 800 plus, and we're going to continue with our calculation, 979.5. Okay, so next, our radiant heat. Okay, let's go to our pointer so I can pull up our charts and our equations. Evaporative loss, radiant heat transfer. Well, radiant heat transfer, it's going to be a little bit of a calculation for us. Radiant heat transfer is equal to some factor based on the amount of clothing or protective gear that the worker is using. We're going to assume fully clothed. I think that's reasonable, right? Times the temperature, the mean radiant temperature, which we're going to have to calculate based on this formula, minus 95. The mean radiant temperature is going to be globe temperature plus 0.13 times the air velocity to the fifth power times the difference between the globe temperature and the ambient temperature. So let's calculate that first, so then we can go up and calculate what R is. Okay, let me move this over. And I'll get my pen. Okay, and we'll go down here. We'll calculate what TW is first. TW, in other words, the mean radiant temperature is equal to the globe temperature, which we know. The globe temperature is 93 degrees. Okay, plus 0.13 times the velocity, which is 130 to the 0.5 power, not 0.6, that was the other formula, 0.5 power, times the difference in the globe temperature and the ambient temperature, which is the globe temperature is 93, ambient temperature is 89, so that's a plus 4. So that's 4. Okay, so we go back to our calculator and calculate this. Let me clear this. So let's see what we have here. I'll start with resolving that exponent, 130. Okay, oops, wrong. Try again, 130. X to the y, and that's going to be 0.5 is equal to 11.4 times 0.13 times 4 plus 93 is equal to 98.9. TW equals 98.9. Okay, so now we can use that to calculate our radiant heat transfer. So our radiant heat transfer is equal to 15 times the difference times the mean radiant temperature, TW, which we just calculated as 98.9 minus 95. So that would be, let's see, 98.9 minus 95 would be 3.9. Okay, so that's going to be equal to a little less than 60. Let's see how that's. Okay, let me get my calculator back. Memory, 15 times 3.9 is equal to 58.5. 58.5. So I'll put 58.5 up here also. And we'll move on with our calculations to our convective heat loss. Okay, convective heat laws. Let's see where we are there. Okay, so that's going to be equal to, convective heat is going to be equal to 0.65 times the air velocity to the 0.6 power times the difference between our ambient temperature and 95 degrees, our temperature that they're basing as a maximum temperature. So let's work on that. So I'll go back here and we'll get our pen, and our convective heat transfer is equal to 0.65 times 1/3, whoops, make sure I get that 0.65, 130 to the 0.6 power times the ambient temperature. Now, the ambient temperature was 89 degrees, which is less than 95. So it's 89 minus 95. It's minus 6. Okay. So let's calculate that with let's go back here to our calculator. Okay, so 130 to the 0.6 power. Okay, times 0.65 times minus 6. I'm just going to multiply by 6. Oh, let me try this again. I think I made a mistake there. I think I might have lost something. 130. As I said, it's a little tedious, but we'll get there eventually. 130 to the 0.6 power. Okay, times 0.65. Okay, 12, that looks right. Okay, times a minus 6. Okay, and that turns out to actually be a negative number, negative 72. So C, oops, C is equal to negative 72. So we'll throw negative 72 up here, and let's do our final calculation here. So we have 800 plus 58.5 plus, minus 72 divided by, I clicked something there again, I think. Let me try this again. 800 plus 58.5 minus 72, 786, and we're going to divide 786 by 979. And that's equal to about 80%. Oh, I accidentally hit something else and it went away, but it looked like it was approximately 80%. Okay, this is equal to this is equal to 0.8. Okay, and if you remember the formula, if you go back to it, you'll remember the formula was times 100 to get a percent. So 0.8 times 100 gives you 80%. Okay, what does that tell us about this whole thing? Let's go back here for a second. What does this tell us about this whole thing? Let's see. Let me get rid of all this writing. What does that tell us? That tells us that our heat stress index was 80% of the maximum. 100%, 100 is 100% maximum heat strain for an acclimatized worker. 70 is severe heat strain. So at 80, we're in the severe heat strain work, but we're not at the maximum heat strain for an acclimatized worker. So the answer to that would be 80%. The final problem in assignment 3, question number 11 asks, how much evaporative cooling capacity do you lose BTUs per hour when the humidity increases from 50% to 90%? Assume dry bulb temperature of 90 degrees and a velocity of 100 feet per minute. Okay, so what this is asking us, it's asking us how much does an increase in the humidity reduce the ability of a worker to cool its body? Okay, so we have some equations for that. Okay, so here we go over here. We have the evaporative heat loss, the amount of heat you can take away from a worker under these conditions by evaporation is dependent on the air movement, is dependent on the temperature of the air, and is dependent on the humidity of the air, or the amount of moisture that the air has in it. We could express that as relative humidity, vapor pressure, grains per pound of air, and so on and so forth, a lot of different ways. But in this case, we're expressing it as millimeters of mercury, okay, in this equation. Okay, so the evaporative heat loss, the amount of heat we can get rid of, is equal to 2.4 times the velocity air times 0 to the 0.6 power times the difference between 42 millimeters and the actual vapor pressure of the moisture in the air. So thing is, though, that this vapor pressure is going to be different, high humidity or low humidity. The velocity and the temperature is staying the same in this case. Okay, so we're going to have to calculate how much this heat loss is affecting us. Okay, so let's see, and actually, just so you, in case you're wondering, the temperature, when we figure out the relative humidity, we know the velocity. If we know the relative humidity, it gives us some insight into what the temperature is, as well as the amount of moisture that's in the air relative to what it can hold. So we have a little bit of a insight into that as well. But really, in this case, we're really focusing not so much on the ambient temperature, but on the heat loss that we can accomplish through evaporation. Okay, so let's give this a try. And I'm going to start by getting a pen and okay, here we go. Okay, so I'm going to take our formula E, and I'm going to start actually solving this equation. Equals 2.4 times 0.06, the velocity, and the velocity is 100 feet per minute, to the 0.6 power times 42 millimeters minus the vapor pressure at, well, our starting humidity is 50%. So we're going to have to figure out what that vapor pressure is at 50%. So but we're also going to repeat this equation at 90%. 100 velocity to 0.6 power times 42 minus the vapor pressure at 90%. And we want to know what the difference here is. How much heat, how much capacity for removing heat by evaporation have we lost when we've increased the humidity to 90%? Okay, but we need to know what the vapor pressures are in order to use this formula directly. Okay, well, fortunately, we have a mechanism for doing that. Okay, and here we go. We can go find our psychometric chart. Okay, and you may remember taking a look at this in class, but we're going to take a closer look at it now. And this is where ambient temperature is going to be relative to us, since we know the humidities, the relative humidities. If you notice, on the bottom here, we have a dry bulb temperature. In our case, it's 90 degrees. And each one of these curved lines represents different levels of humidity. Okay, so we're interested, let's start off with 50% humidity. And if I follow this line down to the point where it crosses that 90-degree line, it looks like it's just about right there. I'm going to bring that up to the top so I can read a little bit better. If I go across to the end, I can see that. Let me get that line on there again. There it is. Got that line right on there. I keep it on there. So right there, it looks like that represents, what does that look like? 18 millimeters of vapor, 18 millimeters of mercury is the vapor pressure of water at that temperature. So I'm going to fill that in there. That would be 18. Now I'm going to repeat that for 90% humidity at the same ambient temperature. Okay, so let's take a look at 90. Okay, 90 degrees, 90% humidity. It's going to be this curved line here, and it looks like an intersection right about where that 0 is. And if I go across, my vapor pressure looks to be 33 millimeters. Okay, you might be able to do this a little bit more accurately than I do, or you might find a reference online or something like that. That'll give it to you a little bit more accurately. But I think, what did I just say? 33 millimeters. Okay, so let's go ahead and find these differences. Okay, so I get my calculator out. Oops. Let me reduce the size of this. So here we go. I'm going to do the first equation. First equation, I'm going to start with that 100 to the 0.6, 100 to the 0.6 power is equal to 15.84 times 2.4 is 38 times the difference between 42 and 18, which is 24, times 24 is equal to 912, a little closer to 913. So I'm going to put that into memory and clear it out here. And I'm going to repeat the calculation with this at this other temperature, at this other vapor pressure and humidity, in other words. And so 100 to the 0.6 power, again, 15.8 times 2.4 times, now the difference here is going to be 42 minus 33, it's going to be 9. So that's equal to 342. And I am going to subtract that from my original vapor pressure, which was, I think it was about 900 or something like that. We're about to get to it. I'm going to say minus. I'm going to change the sign of that to minus, and I'm going to add it to my memory, 912, and it comes out to be about 571. Okay, so I'm going to say 571. So the difference in the amount of heat that I can reject because at the same temperature and the same air movement, because of an increase of humidity from 50 to 90% is 571 BTUs per hour. Just write it down in case you can't hear me. 571 BTUs per hour. And that would be our answer to that question.